Alright, this is a video tutorial about how to complete project number 1. So for starters, you can find all of this information on the MET-121 Blackboard site. It is in the projects folder. Here we see the SOP for projects. We're going to have to stray from this a little bit, given that we're currently in an online format. We'll jump right into the Project 1 folder. Alright, so here I see a tutorial and an exercise. I am going to start by opening up the tutorial. I'll open that up in a new tab. And this is the blueprint that tells us what we have to inspect. Alright, so I see a mostly round part. It has an OD and an ID. It also has a flat on the front. Okay, so our main considerations here are what probe are we going to use? Looks like our smallest diameter is 380 thousandths, and that really drives your probe selection, is what do you need to fit this probe inside of. So it needs to go inside of a 380 thousandths hole. That shouldn't be a problem with our standard 40 by 2 millimeter probe. If we convert 2 millimeters to thousandths of an inch, that would be 2 divided by 25.4. Looks like that's about 78 thousandths. Let's call that 80 thousandths. We have plenty of room to fit that inside of this 380. Another consideration is how long does the probe have to be? This part is only 400 thousandths deep, so we should have no problem if we use a 40 millimeter probe. Again, 40 millimeters long translates to 40 divided by 25.4. Just about 1.5 inches, just over 1.5 inches. So we have plenty of length there. Another consideration is, do we need to index this probe? Do we need to orient this probe at different angles? Really, you ask yourself, are there circular features on multiple sides of the part? If there are, then you would consider using an indexing head probe. For this, we don't need that, so we could just go with our standard A0, B0 probe index, which means the probe is pointing straight down. Alright, so our next consideration is what do we want to use for a fixture plate. So let's download this and take a look at the sample file. So now I'm downloading the ._pi and .cab files. Alright, we'll come into the empty parts list over here and we'll go Part, Restore, and we will restore what I just downloaded. Alright, so this PI and CAB file contain all of the information that we need to know about our fixture. Computer's moving a little slow here, bear with me. Alright, so CAT 1000 is now open. And zoom out a little bit and see how the fixturing is set up. It looks like we have our standard 8 by 12 inch fixture plate. Looks like we have a couple of set screws that are at I10, let's see, J11, and J12. We also have a short Mitutoyo style pressure clamp, and that is held in at E13. Okay, so relatively straightforward with the fixturing. This should give us plenty of access to the part. We do just have to watch out when we're probing this outer diameter here. We'll probably take a couple of hits here, and we just have to be sure to jump up and over the clamp. Also a consideration is the fact that when the operator sets up this clamp, it may be rotated a little bit this way, it may be rotated a little bit that way, so we'll try to steer clear of this entire region of the part, wherever the clamp could potentially be set up. Alright, so next thing is what type of alignment are we using? Well, looking at this, I see that the coordinate system is at the intersection of the top plane, the outer diameter, and it looks like we're going to use this line on the front surface to constrain the rotation. So that is your standard plane circle line alignment. We can use that for both a manual alignment and for an automatic alignment. Now, switching over really quickly to Part Manager, I'm going to open up the manual alignment default program in the editor. And if we double click on Align Coordinate System, we notice that we have 8 default alignments. We have plane, line, line, plane circle circle, plane circle line, a different version of plane circle line, and 4 others. The most common by far are the top 4 options. So in this case, if we look at this a little bit bigger here, let's grab a snip of this. Let's see if we can zoom in on that a little bit. Alright, so it is a little bit hard to see, but if we zoom in closely, we can see we have a plane, a circle, and then a line. The plane is the top surface, the circle is at the, or I should say the origin is at the center of the circle, and then this line here really has nothing to do with our alignment. It just allows us to constrain our C-axis rotation, right? So with that in mind, we do have a standard manual alignment that can be used for this. So we would come into this program in Editor, we would click on our plane, circle, line alignment and say OK. Just say OK to the defaults. Notice that this has changed the align coordinate system from number 1 to number 3. And then we would close out of this, save if prompted, and then we would come in and execute this in repeat mode, and that would establish our manual alignment. All right, so coming back over to CAT 1000, it is important to note that wherever the coordinate system is in this CAD model, you have to match that coordinate system with the manual alignment. All right, now as for our automatic alignment, we would want to touch, let's see, 1, 2, 3, 4 points on the top surface, and then we would say align base plane. We touch 1, 2, we jump up and over the clamp, maybe 3, 4, and 5 points around the outside. Now you could touch 4 points, you could touch 3, you could touch 11. Really I'm touching 5 here because we're not able to touch points that are equally distributed around the feature. So I touch, one more point than I normally would, just to get a better representation of where that circle normally is. And after we touch that circle, we would say actually create origin, and we would create origin in the X and Y axes. That would put our coordinate system at this position here. However, the machine still doesn't know which way the x-axis points until we come back in and touch a line on the front. So we would touch 1, 2, 3 points on the front surface of the part, and then we would say align axis parallel to axis. So many of the same commands that we used for our standard plane, line, line alignment, but when you switch it over to a plane, circle, line alignment, the order of precedence changes a little bit. We'll cover this in more detail in the video on alignments. All right, so by touching those features and putting in those 3 alignment commands, we fully define our coordinate system for this part, and the rest of this program just asks us to measure a couple of features. So looking back at the blueprint, it looks like the only things that we really have to inspect here are balloons 1, 2, and 3. So balloon 1 is the outer diameter. Well, we already inspected that, or I should say we already probed that feature during the alignment. So in the program, we could just output that tolerance right after we touch the feature, even if the alignment is not complete yet. Looks like we've actually touched everything we need to touch for balloon number 2 as well. We already touched this front line as part of the alignment. So we would simply output the position of that front line, and because the coordinate system comes from this intersection point here anyway, we can just output the position of that directly. And then lastly, we just have to touch this ID here. So the only remaining measurement that is required based on this print is we'd probably touch 1, 2, 3, 4 points on the ID, and we would tolerance that right away as well. Okay, so the last thing to consider here, once all of our tolerances are output, we have to review the dimension report, make sure that we've satisfied all the requirements on the blueprint. So we would go line by line, we would check balloon 1 against the dimension report, balloon 2 against the dimension report, and then balloon 3 against the dimension report as well. Of course, you always want to validate any of your measurements using a plate check, and a plate check really just means that you use a precision hand gauge or some sort of manual inspection technique to verify that the results that you've got from the CMM do match within, let's say plus or minus 5 thousandths